Hello everyone, welcome back to the channel. In this video, I am going to start with magnetic circuits. A magnetic circuit is basically path for the flow of flux, or a path of magnetic flux is known as magnetic circuit. The study of magnetic circuit concepts is essential in the design, analysis, as well as the application of electromagnetic devices such as transformers or electrical machines. So when I'm saying electrical machines, electrical machine can be a DC machine or it can be an AC machine. The magnetic circuit basically consists of iron path of specified geometry which will serve as a confined path for the flow of flux. Now this specified geometry can be a square, it can be a rectangle, or it can be in the form of a circle. And that path is actually made up from iron or some alloy of iron or of steel, basically the material which has high permeability or high relative permeability. In order to understand the magnetic circuit concept, I am considering a circular magnetic path. So this path is actually known as core. It is known as core. A coil is wound on this core which is having n number of turns. When we connect the supply across these two terminals, current I will start flowing in this coil. Now this current is flowing through n number of turns. So it will result in the production of flux. Now that direction of that flux can be found with the help of screw rule or right hand thumb rule. According to right hand thumb rule, if the curly fingers represent direction of current, then thumb will give us the direction of flux. Or if the flux is represented by curly fingers, then thumb will give us the direction of current. So basically these are interchangeable. Now when we apply right hand thumb rule in this, what we will see that flux is in upward direction. Flux is in upward direction. Since this is a magnetic path, so flux will remain confined to this magnetic path like this. So flux phi. Now this flux phi is produced only when current is flowing through a coil which is having n number of turns. If there are no number of turns, means if n is 0 then there is no flux. If current is 0 then there is no flux. So basically n into I, they are responsible for production of flux, and this is known as actually magnetomotive force, denoted by mmf. So magnetic motive force is given by n into I, which has units of ampere turns. So this is basically a driving force for the flow of flux through the magnetic path. So we can say this magnetomotive force can be produced when current flow in the coil of one or more number of turns. If number of turns are 0, then magnetomotive force is 0. If current is 0, then magnetomotive force is 0, which is a driving force for the flow of flux. Before moving on to the analysis of magnetic circuit, let's define some other terms associated with the magnetic circuit. The second term is magnetic field strength, or intensity, which is denoted by H. Magnetic field intensity or the strength is defined as magnetomotive force per unit length. Magnetomotive force per unit length. So H is equals to mmf upon mean length of magnetic path. Now if we just look into this magnetic circuit, the flux which is near to the inner perimeter of this circle, that will have less, that has less parameter value, while the outer parameter is more. Outer parameter is more. So we need to find out the mean length of this magnetic path. So if we have a circular or square or rectangular, we always have different parameters for inner and outer of that magnetic circuit. So we need to find out the mean length. So H is basically mmf upon L, where L is mean length of the magnetic path, or we can say of core. So H is equal to Ni by L, ampere turns per meter. All the units must be SI units. Then we have magnetic flux density, which is denoted by B. So this magnetic flux density is actually flux per unit cross-sectional area. So this AC is the actually cross-sectional area of the magnetic path, cross-sectional area of this. So if flux phi is flowing through this, then we can find out the flux density. We also know that the flux density is related to the magnetic field intensity by relation B is equals to mu into H, where mu is equals to mu naught into mu r H. Now we have the value of H as Ni upon L. So B is equals to mu naught mu r Ni by L. Also B is equals to phi upon AC. From here B is equals to phi upon AC. So phi upon AC equal to mu naught mu r Ni by L. If we consider phi on this side, take AC to the other side, then we have the equation as this, where we can write phi equal to Ni by L upon mu naught mu r AC. So the term which is here in the denominator, this is known as reluctance. This is known as reluctance, which is denoted by S or by curly r. So S is equal to L upon mu naught mu r AC. Phi is equals to Ni by S. Now phi flux is the response, Ni is the driving force, and this S, which is reluctance, this is the opposition offered to the flow of flux. So this relationship is quite similar with I is equals to V upon R, where V is the applied voltage, R is the opposition offered to the flow of current, and current I is the response of this applied voltage across any electrical circuit. Similar to resistance, reluctance is dependent upon the physical parameters. It is dependent upon the mean length of core, cross-sectional area of the core, relative permeability, mu r, that depends upon the material, and mu naught is the permeability of free space, given as 4 pi into 10 raised to power minus 7. Now, in this magnetic circuit, it was a solid core. We can have the possibility that this magnetic circuit is having some gap like this. Is having some gap. Again, a coil is wound on this. Current I is flowing. When we apply right hand thumb rule, flux will flow through this magnetic path. Now, the flux will have to pass through this gap, which is known as air gap. It is known as air gap. The air gap is usually very small in comparison to the mean length of the core. Now flux has the property that it can pass through the air. But the reluctance of the air, that will be different from the reluctance of core. So we can draw an electrical equivalent of this circuit. So here we have MMF N into I, that can be represented like a source. Then we have reluctance of the core, the reluctance of the air gap, and flux phi is flowing through this. So it's just like a series circuit. The reluctance is represented by same symbol as the resistance. Now we can calculate this flux as MMF upon total reluctance, which is SC plus SAG. So it's just like a series circuit. Now we can see that here we have air gap. The flux can remain confined to this path, or it can even bulge out like this over here. This bulging out effect is known as fringing. And for according to this effect, if fringing is taking place means flux is bulging out, then the effective area is increased now. Effective area is increased, so that will actually decrease the flux density in the air gap. And usually in magnetic circuits, this air gap is so small that fringing can be neglected. Also, we are assuming that whole of the flux is flowing through this magnetic path. It is following this confined path only, but there is possibility that some of the flux is leaking, which is known as leakage flux. Basically, the flux which is not passing through the magnetic path, it is flowing through the air gap, or the not air gap, passing through the air which is surrounding this coil. This is known as leakage flux. So the value of leakage flux is quite small, since the opposition offered to the flow of flux by the air is much higher in comparison to the reluctance offered by the core. This can be clear from the expression of reluctance, since the relative permeability of air is 1, while for the electromagnetic materials it's in the range of thousands. So the reluctance of the magnetic material is much less in comparison to air. That's why the flux mostly flows through the confined path instead of flowing through the surrounding air. Now, in case of magnetic circuits, we can have series circuit like this, or we can have even the possibility that there are two different paths for the flow of flux. We can have a magnetic circuit of shape like this. Now this circuit may have an air gap or may not. It's not always essential to have an air gap. If this is a circuit, let's say the coil is wound on this side of the core. This is known as limb. This is also known as limb, or this is also known as limb. If coil is wound on this n number of turns, the flux will flow in upward direction. This is the direction of flow of flux. After this point, the flux has two options. It can flow either through the central limb, or it can pass through the outer limb and then come back. So this will be the complete path. So basically there are two paths. Some of the flux will follow this path. Let's say this is phi 1. This one is phi 2. Then over here again we have phi. So phi is actually phi 1 plus phi 2. So this is similar to the parallel circuit. We can draw its electrical equivalent, like we have a MMF source over here as Ni. Then we have the reluctance of this area starting from here up to here. If this point is A, this one is B, This one is C, D, E, and F. Then this is the reluctance. S, A, F, E, D. Reluctance from A to D. Then we will have reluctance from A to D. Then the reluctance is A, B, C, D. Flux phi, phi 1, phi 2. Since these two magnetic circuits, this and this, they are connected in parallel. So the MMF drop across these two reluctances will be same. Means SAD into phi 1, it will be same as SABCD into phi 2. And that will be equal to this MMF minus drop across this into phi. So it's just like an electrical circuit in which we have branches connected in parallel. So based on this discussion, we can drive the analogy between electrical and magnetic circuit. Now in case of electrical circuit, the driving force is potential difference, while in case of magnetic circuit, the driving force is MMF. So we can say here we have EMF. EMF is analogous to MMF, or MMF is analogous to EMF. So this is a driving force. Then the response in case of electrical circuit is current, while in case of magnetic circuits the response is flux. In case of electrical circuits, the opposition offered to flow of current is resistance. The opposition offered to flow of flux is reluctance. So both are analogous. In case of electrical circuits, we have electric field intensity, which is actually defined as electric potential gradient, means EMF per unit length, or potential difference per unit length. While in case of magnetic circuits, we have magnetic field intensity, which is MMF per unit length. So electric field intensity is analogous to magnetic field intensity. Then another similarity or analogy between these two is voltage drop and MMF drop. The voltage drop is equals to I into R, while in case of magnetic circuits we have MMF drop, which is phi into S. In case of electrical circuits, we have current density, which is current per unit area, and in case of magnetic circuits, we have magnetic flux density, which is flux per unit area. So these are the similarities starting from the driving force to response and opposition. We can have the differences also. We can say the distinction between magnetic and electric circuits. Now, the very first distinction is in case of electrical circuits, current cannot flow through the air, but the flux can flow through the air. So, this is a major difference between these two. Second difference is the magnetic flux lines are actually imaginary while the current flows because of flow of electrons. Third difference is the resistance in case of electrical circuit is dependent upon temperature while the reluctance is independent of temperature. So these are the major differences between electrical and magnetic circuits. All the laws such as Ohm's law, which is equal to V into IR, its analogy in case of magnetic circuit is MMF is equals to flux into reluctance. It is equally applicable. Series and parallel formulations are similar in case of electrical and magnetic circuits. In the next video, I will solve the problems based on the magnetic circuits. Thanks for watching this video.